Hello, Applied Physics students. Here are some corrections for homework number 11 if you need them. So, number 10, what is the meaning of free fall? Right? Free fall is that an object is falling under the force of gravity and no other forces, okay? Your textbook says fall is free of air drag and forces other than gravity. So the only thing that's acting on an object in free fall is gravity. Number 11, for a freely falling object dropped from rest, what is the instantaneous speed at the end of the 5th second of fall and the 6th second? So I want to know my velocity or speed, right? I can use those interchangeably when the time equals 5 seconds and when the time equals 6 seconds, okay? When I am in free fall, okay, my velocity, I have an equation for that. The velocity is gt. So g is our acceleration due to gravity, which is 10 meters per second squared, times our 5 seconds, gives us 50 meters per second, and it would be downward. For the second one, again, we still use the same equation. Again, our acceleration due to gravity is 10 meters per second squared, and it's 6 seconds, so it would be 60 meters per second downward for number 11. Number 12, for a freely falling object dropped from rest, what is the acceleration at the end of the 5th second? So we want to know acceleration this time. When our time is 5 seconds. When our time is 6 seconds, the 6th second, and at the end of any elapsed time t. This really is a little bit of a trick question, right? Because the only thing that's acting to accelerate this is gravity. So the acceleration is constant. And again, it's the 10 meters per second squared downward. Okay? Your textbook answer has the 9.8 meters per second squared. But again, we're using 10. So it's 10 meters per second squared at 5 seconds. It's 10 meters per second squared at 6 seconds. It's 10 meters per second squared at any time. So it doesn't change. Number 13. Okay. How far will a freely falling object fall from rest in 5 seconds, 6 seconds? So how far, remember, is asking us about distance. And again, our time is going to be 5 seconds. And then our time again is going to be 6 seconds. And so our equation for free fall for distance is 1/2 gt squared. So 0.5 times 10 meters per second squared times our time, which is 5 seconds, squared. So again, we put that in our calculator, 0.5 times 10 times 5 squared, and that gives us 125 meters. We do the same thing for the other time, so here's my equation, 0.5, 10 meters per second squared, and it's 6 seconds squared. So 0.5 times 10 times 6 squared, okay, gives us 180 meters. Number 14. How far will an object move in 1 second if its average speed is 5 meters per second? So our average speed or velocity is 5 meters per second. We want to know how far, so we want to know our distance. Okay, our time is 1 second. And so this is where we use that equation, okay, about our average velocity being our distance, or sorry, let me fix that. We're looking for our distance. So we're going to we're saying, again, this can be also speed. So we can use our manipulation of our speed equation, which is that our distance equals our speed times our time. So our speed is 5 meters per second. Our time is 1 second. So that gives us 5 meters for number 14. Number 15. How far will a freely falling object have fallen from a position of rest when its instantaneous speed is 10 meters per second? So we're asking again for our distance because it's asking how far. From a position of rest, so our first velocity is going to be 0 meters per second. And when its instantaneous speed, so its velocity is 10 meters per second. Okay. So this kind of uses this idea that we can use how far will it have fallen from a position where its instantaneous speed is 10 meters per second. So if we could kind of think about this with a picture, right? Here's our object and it's not moving. Now it's moving 10 meters per second. Now, what time frame was that? Well, we should know, right, that this is 1 second because we know that we pick up 10 meters of second of speed each second we go. That's the acceleration due to gravity. So we kind of know that our time is 1 second here. So then we could do our d equals 1/2 gt squared, 0.5 times 10 meters per second squared times 1 second squared, right, which gives us 5 meters for number 15. Okay. All right, so from number 15, the next one you had to do was number 18. Number 18 says, does air resistance increase or decrease the acceleration of a falling object? So remember, we're ignoring air resistance, but if there was air resistance, if we were taking it into account, would it increase the speed or decrease the speed? Okay. And again, air resistance would decrease because it's going to be like friction against the object and it's going to slow it down. It's going to act opposite the direction of gravity. So it would decrease the speed. Number 19. What is the appropriate equation for how fast an object freely falls from a position of rest? For how far that object rests. So our velocity equation is gt, and our how far, which is distance, is 1/2 gt squared. So that was just asking for those two equations in number 19. Number 21. Below we see before and after snapshots of a car's velocity. The time interval between before and after for each is the same. So, letter A, rank the cars in terms of the change in velocity from most positive to most negative. Negative numbers rank lower than positive ones, and remember, tie scores can be part of your ranking. So, our change in velocity. Okay, so our equation for change in velocity is our kind of second velocity minus our first velocity. So in letter A, we have 20 meters per second minus 10 meters per second, which gives us 10 meters per second as our change. In letter B, which is below it, we have 10 meters per second minus 0 meters per second, which gives us 10 meters per second. So those two will be equal to each other. Letter C, we have our final velocity is 15 meters per second. Our initial is 20 meters per second, which gives us a negative 5 meters per second. And letter D, we have 15 meters per second minus 15 meters per second, which means we have a 0 meters per second. And these, again, are our changes in velocity. So for 21, the first part of this is part kind of A, right? The most is, okay, right, so, sorry, I was looking at the answer key and I think there's a mistake in the answer key. So for 21, we want to rank the cars in terms of change in velocity from most positive to most negative. Most positive, we have A is equal to B. Then we have D. Then we have C. Okay. Part B, right, asks rank them in terms of acceleration from greatest to least. Acceleration is our change in velocity over our change in time. So our answers really are going to be the same because this is staying the same. So it's really going to be, the most acceleration is going to be the biggest change of velocity. So it's going to be A equals B, D, and then C again. Next we do number 22. Number 22. These are drawings of same size balls of different masses thrown straight downward. The speeds shown occur immediately after leaving the thrower's hand. Ignore air resistance. Rank their accelerations from greatest to least. Or are the accelerations the same for each? So, again, this is kind of a trick question because remember, it doesn't matter how fast the balls are moving initially. This is asking about acceleration, which is their change in velocity over their change in time. The only force that's going to be acting to change their velocity is gravity. And gravity is going to work the same on all of them. So for all of them, their acceleration is the acceleration due to gravity, which is 10 meters per second squared. So, the correct answer is to say that they're all equal to one another. It doesn't matter how fast they're moving initially, the rate at which they're going to pick up speed will be the same. Now, this would have been a different answer if it asked how fast they were moving, but it asked about their acceleration, which is all due to gravity. Our next question is number 26. Number 26 says, calculate your average walking speed when you step 1 meter in 0.5 seconds. So again, our equation is that our speed is our distance divided by our time. Our distance is 1 meter. Our time is 0.5 seconds. So again, on our calculator, 1 divided by 0.5 is 2 meters per second. Number 27. Calculate the speed of a bowling ball that moves, okay, so we want speed again. That moves 8 meters, that's our distance, in 4 seconds. So speed equals distance over time. Our distance is 8 meters. Our time is 4 seconds. 8 divided by 4 is 2 meters per second. 28. Calculate your average speed. Okay. So our speed is what? If we run, distance is 50 meters in our time of 10 seconds. Again, our speed still is our distance over our time, 50 meters over 10 seconds. 50 divided by 10 is 5 meters per second. 29. Calculate the distance in kilometers. So we want a distance that Charlie runs if he maintains an average speed of 8 kilometers per hour for 1 hour. So again, our equation for distance is our speed times our time. Our speed is 8 kilometers per hour. Our time is 1 hour, which gives us a distance of 8 kilometers. Number 30. Calculate the distance you will travel if you maintain an average speed of 10 meters per second for 40 seconds. So again, our distance is our speed times our time. Our speed is 10 meters per second. Our time is 40 seconds. So 10 times 40 is 400, okay, meters. So our distance will be 400 meters. Number 31. Calculate your distance in kilometers. You will travel if you maintain an average speed of 10 kilometers per hour for time equals 0.5 hours. So again, our distance is our speed times our time. Our speed is 10 kilometers per hour. Our time is 0.5 hours. So 10 times 0.5 is 5 kilometers. Number 32. Calculate the acceleration of a car in kilometers per hour per second that can go from rest. So our first velocity is 0 to a final velocity of 100 in a time of 10 seconds. So our equation for acceleration is our change in velocity over our change in time. So our change in velocity is 100 kilometers per hour minus 0 kilometers per hour divided by the 10 seconds, which is basically 100 kilometers per hour over 10 seconds. 100 divided by 10 is 10. So it's 10 kilometers per hour per second. Number 33. Calculate the acceleration of a bus that goes from, again, our initial velocity is 10 kilometers per hour to a speed of 50 kilometers per hour in a time of 10 seconds. So again, our acceleration is our change in velocity over our change in time. So we are ending at 50 kilometers per hour. We started at 10 kilometers per hour, and we did that change in 10 seconds. 50 minus 10 is 40. Divided by 10 seconds gives us 4 kilometers per hour per second. Number 34. Calculate the acceleration of a ball that starts from rest. So our initial velocity is rest. It looks like we're going to be measuring this in meters per second. And rolls down a ramp and gains a speed of, so its second velocity is 25 meters per second, and the time is 5 seconds. So again, acceleration is our change in velocity over our change in time. So 25 meters per second minus our 0 meters per second divided by our 5 seconds. We have 25 meters per second divided by 5 seconds. 25 divided by 5 is 5. Okay, meters per second squared this time because we have 2 seconds there. After number 34, we're skipping to number 37. Number 37, calculate the instantaneous speed of an apple 8 seconds after being dropped from rest. So again, we kind of want its speed or velocity. Our time is 8 seconds. Okay, and so again, this is that free-falling equation where our velocity is our acceleration due to gravity times our time. Our acceleration due to gravity is 10 meters per second squared. Times our 8 seconds gives us 80 meters per second for number 37. Next, we're doing 38. On a distant planet, a freely falling object has an acceleration of 20 meters per second squared. Calculate the speed of an object dropped from rest on this distant planet acquires in 1.5 seconds. So again, our velocity is our acceleration due to gravity times our time. Now, this time we're on a different planet, so our acceleration is actually 20 meters per second squared. They told us that in the problem. Our time is 1.5 seconds. So 20 times 1.5 gives us 30 meters per second for number 38. 39. A skydiver steps from a high-flying helicopter. If there were no air resistance, how fast, so we want to know his velocity, would she be falling at the end of a 12-second jump? So we're back on planet Earth, so our equation is V equals GT. We're back on Earth, so our acceleration due to gravity is back to being 10 meters per second squared. Our time is 12 seconds. So 12 times 10 is 120 meters per second for number 39. Number 40. Calculate the vertical distance an object dropped from rest would cover. So vertical distance is asking about us distance. In 12 seconds, if it fell freely without air resistant, okay, and we know that it's starting at rest, so we can use that equation D equals 1/2 GT squared. So 0.5, G is still 10 meters per second squared. Our time is 12 seconds, and we have to square that. So 0.5 times 10 times 12 squared gives me 720 meters for number 40. Number 41. An apple drops from a tree and hits the ground in 1.5 seconds. Calculate how far it falls, which is a distance, and again we're on Earth, so our distance is 1/2 GT squared. 0.5, G is on Earth, so it's 10 meters per second squared, and our time is 1.5 seconds, and we have to square that. So 0.5 times 10 times 1.5 squared gives me 11.25 meters. After 41, we're going to skip to number 43. 43, letter A. If a freely falling rock were equipped with a speedometer, by how much would its speed ratings increase with each second of fall? Right, so it's saying we have our rock and it's each second. What would its speed change by? Well, again, that has to do with acceleration being 10 meters per second squared. So its velocity would change by 10 meters per second each second. Okay, so 10 meters per second. Part B. Suppose the freely falling rock were dropped near the surface of a planet where g equals 20 meters per second squared. By how much would its speed readings change each second? Well, now, again, our velocity is still going to change by our acceleration due to gravity, but now it's 20 meters per second each second. So it would change by 20 meters per second. Number 44. Which has more acceleration when moving in a straight line? A car increasing its speed from 50 to 60. So we have our car with our first velocity 50 kilometers per hour and our second velocity being 60 kilometers per hour. Or a bicycle that goes from 0 to 10 kilometers per hour in the same amount of time. And so the question is, which has more acceleration? Right? And again, our equation for acceleration is our change in velocity over our change in time. Our change in velocity is kind of our final velocity minus our first velocity divided by our change in time. So for the car, right, that's going to be 60 minus 50 divided by, we'll just make it 1 second because that makes it easier, right? So that's 10 kilometers per hour per second. For the bike, our acceleration is 10 kilometers per hour minus 0 kilometers per hour in 1 second. So we have 10 kilometers per hour per second. So it's a trick question again, right? Their acceleration is the same because their change in speed is the same for the same period of time. Number 45. Correct your friend who says the dragster rounded the curve at a constant velocity of 100 kilometers per hour. Here's the deal, right? Velocity is a vector quantity, which means it has both a size and a direction. So although the speed, okay, the magnitude stays the same, because we're going around a curve, we're constantly changing direction. So we could kind of correct it a couple different ways. Number one, we could say the dragster rounded the curve at a constant speed of 100 kilometers per hour. Or the dragster rounded the curve with a changing velocity of 100 kilometers per hour. Your textbook said constant velocity means constant direction. So your friend should say at a constant speed of 100 kilometers per hour. Our next question is number 47. Tiffany stands at the edge of a cliff and throws a ball straight up at a certain speed and another ball straight down with the same initial speed. So we're on the edge of a cliff. She throws a ball straight up. She throws a ball straight down. Okay, and their speeds are the same. Okay, when they start. Neglect air resistance. Letter A. Which ball is in the air for the longest time? Well, obviously, the ball that we would throw up in the air is going to be in the air longer than a ball we throw straight down. So for 47, okay, the ball thrown upward will be in the air. For a longer period of time. Letter B. Which ball has the greater speed when it strikes the ground below? This is a trick question, right? This ball, when it goes upward, it's going to lose speed until it hits the top, and then it's going to gain speed as it comes back down. But it's going to have the same speed here going down as it did going up, which means both balls, when they're headed down, have the same speed, which means, okay, they are both going to strike the ground with the same speed. Okay, so both hit the ground with the same speed. When the upward ball returns to its original level, it has the same speed as the ball thrown downward. 48. A ball is thrown straight up. What will be the instantaneous velocity at the top of its pass? So we're throwing our ball straight up. We want to know right up here, before it starts to come back down, what is its instantaneous velocity, right? And its instantaneous velocity is going to be 0 because it's momentarily at rest. What will be its acceleration at the top? Well, there's still gravity acting on it, right? So its acceleration is still equal to gravity, which is still 10 meters per second squared downward. Okay, why are your answers different? Because, okay, velocity and acceleration are different. Your textbook answers it this way. Concepts of velocity and acceleration differ. Okay, so they're different ideas. All right, almost done. Number 51. A dragster going at 15 meters per second north increases its velocity to 25 meters per second north in 4 seconds. So our velocity, our first velocity is 15 meters per second north. Our second velocity is 25 meters per second north. And it does that in a time of 4 seconds. What is its acceleration during this time interval? Acceleration is our change in velocity over our change in time. So 25 meters per second minus 15 meters per second divided by our 4 seconds. 25 minus 15 is 10 meters per second over our 4 seconds. So 10 divided by 4 is 2.5 meters per second squared, and I can have a direction here, and acceleration should have a direction, and I know it's north because both of my velocities are north. And our last question is number 52. 52 says, an apple drops from a tree and hits the ground in 1.5 seconds. So time is 1.5 seconds. What is its speed just before it hits the ground? So we want to know its velocity. And again, we're dropping from a tree, so it has to be the acceleration due to gravity. So our velocity equation is our g times our t. 10 meters per second squared for our acceleration due to gravity, 1.5 seconds. 10 times 1.5 is 15 meters per second, and again, it's moving downward. So our acceleration would be 15 meters per second downward. And that's the end of your homework. I hope if you had some questions on your homework, that has helped you out. Have a great day. I'll talk to you tomorrow.